Today we're going to talk about functions and change, and we want to begin with this question, what is a function? So in a math class, typically you'll see a function denoted f of x, and then after f of x you'll see some sort of expression to follow like x squared. And the point of this is that if you plug in a number for x, like f of 3, on the right you have the rule which says square 3, and so you get out 9. Really, in essence, what a function is, it captures this idea if you put something in, then you get something out. Now the trick here is that you can put lots of things into a function. This example that I gave you right here is a function of one variable, but you certainly can have a function of two variables. We could write f of x comma y, and we could say, let's just make it x plus y. And so if you plug in, let's say we plug in 3 for x, and we plug in, let's say 2 for y, this is actually just 3 plus 2, which is 5. So this one is an example of a function of two variables. The trick with the function is you can put lots of things in, but you just get out one thing. And this allows us to be able to work with these things. All right, so you can put lots of things in, but you just get out. All right, so just get out one thing. All right, so that's sort of something you have to watch out with functions. Let's look at an example of this. Here are a bunch of graphs that we want to look at. Some of these graphs are functions, and some of them are not. And we want to determine which of the following graphs are actually functions. So if you look at the first one, the inputs lie along the x-axis here, and the outputs lie along the y-axis. So if you put in an input here, you get up out here, and here's the output. And you notice if you put one thing in, you get one thing out. Here, the same thing occurs. If you put one thing in, so put this in, and you get this out. Over here, if you put this input in, you get this out. You have to remember the way that we define a graph. So how do you define a graph here? And this graph here, the idea is that here's an input, and then here's a point on here, and so this is the output. So it goes input, comma, output. That's basically how you define a graph. 3 is a first example where it is not a function. And the idea is if you put one thing in, you do get something out, but you don't just get one thing out, you get two things out. So this is not a function. So not a FCN. And same thing in 4, it's not a function, because again, let's look over this side, you put one thing in, so you put something in here, you don't get one thing out, you actually get two things out. And then this is a function. So if you put in one thing, you certainly get out just one thing. So 1, 2, and 5 are examples of functions, whereas 3 and 4 are not functions. Now, even though 3 and 4 are not functions, you can still make 3 and 4 into functions. One way to do this, if you look at, let's look at this one here, number 3, you can make this into a function by just considering the upper part of the circle, so the half circle. And then you can consider the one on the number 4 here by considering just these upper parts here, so in blue. So these are now functions if you just consider the green part and the blue part. But when you consider the whole piece, the whole circle, it's not a function. And this is actually hyperbola. When you consider the whole hyperbola, it's not a function, at least in this case. We also want to talk about functions. We're going to talk about functions from two different points of view. From the point of view of a graph versus a formula. We'll also look later in the course at functions from the point of view or from the perspective of a table and words by itself. And when we talk about these point of views, the first thing we want to look at are the domain and range. And so the domain, it's a very simple idea. The domain is a set of all possible inputs for your function. Whereas the range, well, if the domain is the inputs, the range is the possible outputs. So it's important to be able to identify what's going to go into your function, and then hopefully, if you can, identify what's going to come out of it. And we're going to do this two ways. First, we'll look at a graph, and then we'll look at a bunch of formulas. So let's take a look at the graphing part. So we want to find the domain and range of the following function. So to figure out the domain, you want to look along the x-axis because these are all the possible inputs. And so what I would write here, and we're going to use what's called interval notation. So we'll say the domain, and we'll use the letter D for domain, is equal to, and now the domain is good all the way to the left because this arrow goes down, so the domain's good here, 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 and then it stops right there, and I bet that's probably 1/2. So my domain would be the interval from -infinity to 1/2. And we're going to use a closed bracket, and the closed bracket says we include 1/2 here. So these are my possible inputs. The range now, to the possible inputs, these are the possible outputs. Outputs lie along the y-axis, and to see these, let's use red. And we start down here. Now it goes all the way down, so these are all good outputs. We hit all these points. But we stop up here at number 2. It doesn't look like we go past number 2 because as you go up here to 3, let's say, you look to the left or the right, there's no graph. So it's not in my range. You can never hit an output of 3 because the graph does not go there. And so my range would be equal to -infinity all the way up to +2, and we'll include it. Now you can change this problem a little bit, and you can change the possible domain. So let's suppose this is a closed circle. Instead of a closed circle, let's suppose it was an open circle. And then my new domain would be -infinity to 1/2, but instead of a closed bracket, I'd put a parenthesis here, which means don't include 1/2. I could also change the range by putting an open circle right here. So now that's an open circle, and so my range would now be -infinity, and I would still go to 2, but instead of including 2, I could cut it out because that's an open circle, which means do not include. So that's another example of the domain and range if you change the graph a little bit. Let's take a look at finding the domain from just a formula because it's a little bit different. So when we work with formulas, there's basically going to be 3 things that we have to worry about. And up front, there's just going to be 2. So the first thing we have to worry about is that you never want to divide by 0. So this is my way of saying you can't divide by 0. And then the second thing is if you have an even root, like a square root, so this is any even root, so square root, 4th root, 6th root, 8th root, and so on, you have to make sure that this is bigger than or equal to 0 underneath the radical sign. And the reason for this is we do not want to consider numbers like the square root of -1, because if we do this, then we have to start talking about what are called complex numbers. So complex numbers. And all we're going to deal with in this class are real numbers. So we do not want the square root of negative numbers or the 4th root or 6th root or so on. And then eventually here, we'll talk about the third rule when we talk about logarithmic functions. If we have an ln function, we're going to need to make sure that this is actually bigger than 0. We'll see that you can't take the ln of a negative number. But all we have to worry about in these problems right now are 1 and 2. So if you look at part A, and we're trying to figure out the possible inputs, the things we can put in to the function, you look at this and you ask yourself 2 questions. Is there a denominator? And you say no, so you don't have to worry about 1. And is there a square root, 4th root? Is there an even root? And you say no. And since it does not satisfy 1 or 2, you know the domain can be anything. And if you think about it, that should be obvious. Certainly you can plug in any number in for x and square it and get back another number. Nothing's going to stop you from squaring a real number. In part G, let's look at it. Now you ask yourself the same questions again. Is there a denominator? You say no. Is there a root? You say yes. So there's a square root, so you need to make sure that x minus 2 is bigger than or equal to 0. Because that's what the rule says, basically. You don't want to deal with complex numbers, so make sure that's bigger than or equal to 0. We can solve this inequality by adding 2 to both sides. So x is going to be greater than or equal to 2, which means you can draw a sign diagram. And so that means you start at 2 and go all the way to the right. So my domain D is going to equal 2. We want to include it because x could be 2. If x is 2, notice that's going to be the square root of 0, which is 0. And all the way to infinity. And then finally, part C, we have this function, h of x equals x squared plus 1 divided by x squared minus 1. And we ask ourselves the question, is 1 an issue? And we say yes, because there's a what? Hopefully you say there's a denominator. So we need to make sure that the denominator is never 0. So we do not want x squared minus 1 to equal 0. So we go and look to find out when it's equal to 0. So when is x squared minus 1 equal to 0? I'm going to factor this, so you get x minus 1 times x plus 1 equal to 0. And if you have two things and you're multiplying them together and getting back 0, one of the things has to be 0. So this times that is 0. Either x minus 1 is 0, or x plus 1 is equal to 0. And so let's solve these two equations here. So you're going to get x equal to 1 when you add 1 to both sides, or x is equal to negative 1. And so you can draw a sign diagram if you want here. So I'll take out negative 1 and 1. So when you take out, I draw a big circle here, an open circle. And I know it can be any numbers except for negative 1 and 1. Realize it does not satisfy 2. You don't need to worry about it. There's no radicals. And so my domain D would equal all numbers to the left of negative 1, but don't include negative 1, so I draw a parenthesis here. Then I'll draw this symbol, which is a U for union, and then I go from negative 1 to 1, then union, so that's the middle piece, then union 1, comma infinity. And so that's my domain for C. Now how about the range? The range is a lot harder to find, and typically you cannot find the range from a formula in general. You really need to graph it. But some ranges are simple to find depending on what type of formula is given to you. So like this range here of this function, what are the possible outputs? So remember, domain are the possible inputs, whereas the range are the possible outputs. So notice when you square something, it's always going to be positive. So for this one, my range are all the positive numbers, and including 0, because if you plug in 0, you get out 0. So I know my outputs are 0 to infinity. And again, the way I found that is I have to look at the specific function and see if I can't figure out properties about it. And this one, you're squaring it. I know if you square something, it's always positive. So I get out all the positive numbers, plus I get out 0. And then for this one, the square root, I know it's always going to be positive, because if you take the square root of something, it's always positive. It can never be negative. And again, I know I can get out 0, because if I plug in 2, 2 minus 2 is 0. So I'm going to guess that this is probably also 2 to infinity, because as I increase x, I make it 3, I get the square root of 1, 4, I get the square root of 2, and so it's going to keep going up. So the possible outputs will run from 0 to infinity. Now this last one right here, part C, this one, I'm not going to be able to do this one unless I actually graph it. So if you have your calculator handy, take it out, and I'll show you. Most of the time, we have to graph these things to figure out the range, because it's not obvious what exactly is occurring. And so on your calculator, you can graph this function by hitting y equals, and then plugging it in. So left parenthesis, x raised to the 2 plus 1, and end parenthesis, then divided by left parenthesis, x raised to the 2 minus 1. And then I'm going to make my window. Now, I know I have problems at -1 and 1 because in my domain I can't plug those in. So what I'm going to do is I'm going to go a little bit left to -1 and a little right of +1. And I'm even going to set my y-min. I'm just going to make it -10 to 10. That should give me a good looking window. And I chose -10 to 10 because that's the standard sort of choice we typically use in a math course. And so you can kind of get an idea of what's going on. So for my range R, what I would actually say is it looks like it goes all the way down. So R is going to equal, I go to -infinity. But there's going to be some issues. When I trace this thing, you can see that y is going to go up just to -1. So it's going to go up to -1, union, and then it's going to jump. It's going to jump up here, and then the graph on the left and right are going to go down. And it looks like they're going to go down, and they actually don't go down to 0. If you trace this and you hit over, let's get over here. I'm going to plug into enter, and I'll get over here. It's going to go over to the right, but it's actually not going to ever hit 0. It's actually going to approach 1, and that's hard to see. And we'll learn later on how we can actually do this with calculus. How we can see that the limit, as x gets bigger and bigger, my graph is actually, the height of my graph is actually going to approach 1. So what I would probably do here is I'd probably draw a left parenthesis, and I'm going to go from 1, and then I'm going to reset my window here because I don't like what happened. So -2 to 2, and then -10 to 10. All right, so you can see it again. So it's going to go from, let's make this jump from -1 to 1, and then it's going to go up to positive infinity, because you can see here as it goes all the way up, all the way up. Now, I would not expect you to be able to do this one starting off right now, but later in the semester we'll learn another way to look at this to try to figure out, what are the possible outputs. These have what are called vertical and horizontal asymptotes, and we'll learn about that later in the semester. The last thing we want to look at is how do functions change.
They basically change in two ways. They can either increase or decrease, and they can increase and decrease by either being concave up or concave down. So let me talk about these two ideas. So if a function is increasing, hopefully you know that it's going up. So this is what we mean by increasing. Whereas when a function is decreasing, it's going down. Now, when you increase or decrease, there are different ways to increase or decrease. In some sense, you could increase in a concave up manner. So you might look something like this. This is concave up. Or in a concave down manner. So this is concave down. And for right now, the way I would remember these two, if a function is smiling, it's concave up. If a function is frowning, it's concave down. And when we have this concave up and concave down activity, we often get what are called local minimums or local maximums. I guess I should say when you get increasing to decreasing, you get a local maximum. So like this one here, you increase and then you decrease, so this becomes a local max. Whereas down here, this is, of course, a local min. We use the term local because you could have lots of maximums and minimums locally. So if you look at this graph right here, you can see that we have how many local maximums. Well, locally, this is a maximum. Locally, this is a maximum. And locally, that's a maximum. So you have 3 local maximums. Later on, we'll talk about global maximums and global minimums. The idea of global means it's overall the highest point on the graph. It would be the global maximum. The global minimum would be overall the lowest point on a graph. Concave up and concave down leads to what are called inflection points. So let me just give you a real quick example. So if you change concavity, you're going to get an inflection point. So on this graph right here, an inflection point occurs somewhere from going concave down, CD, to concave up. And so we call this green point right here the inflection point. You can define it, for us, we'll just define it as the point where the graph changes concavity. So there's a change in concavity. And you can convince yourself of the existence of this point. This is obviously a frown, so it's concave down. This is obvious smile, so it's concave up. So there should be some point on the graph which is neither a smile nor a frown, because you're going from a frown to a smile. And so that point right there is the inflection point. Let's do an example. So in this example, we want to determine how functions change. And so to do this, we're going to find where this function on the right is increasing or decreasing, local mins, local maxes, concave up or concave down, and identify all the inflection points. So let's start here. So for increasing, we always read a graph from left to right, just like you read a book. And so it's obviously, even though the arrow points down, from left to right, it's going up. So it's increasing and increasing, increasing, increasing all the way up here. And then it begins to decrease, so it decreases, 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 decreases. Here we have a little bit of an issue, which I'll talk about in a minute, but then it obviously is decreasing here. So for increasing, a function is increasing on what interval? And so we always do the inputs, so it's increasing all along here until you get to about -1, it looks like. So it's increasing from negative infinity to -1, so this is interval notation. And then after that, it looks like it's decreasing, so it's decreasing from -1 until you get right here, which is the point 0. So it's going down from -1 to 0. Union, and it continues to decrease after that until you get to about, let's say, 1/2. So then from 0 to 1/2. At 0, you sort of have this issue. If you think about it, what's kind of going on here is it's decreasing, but then it's leveling out here at the origin. And so that's really a point that's not increasing or decreasing, and so we typically won't include it. If you did include it, I don't know, I mean, there are definitions that we can come up with that it might include that it's actually decreasing there, but I would say it's leveling off, so it's not decreasing there. So I'd prefer you not include that point. For local mins and local maxes, well, it's obviously that this is a max, local max, and then down here, this is a low point, and so this is a local min. And so on here for our local mins, we could put, let's say f of, if you plug in 1/2. So if you plug in 1/2, it looks like you get out a nice point between 0 and -1, so let's say -1/2. So you get out -1/2. I think it's good to say the input and the output. The local minimum and local maximum are actually just the outputs, but I think it's good to give both. For the maximum, the input is this -1 here, which is hard to see, but it's right there. So f of -1, and the output is equal to the height of 2. So those are my local minimums and my local maximums. All right, let's do concavity now. Now when we do a concavity, let me erase this so we can kind of start over. So for concavity, I'm looking for where the function is frowning versus smiling. So concave down is a frown, concave up is a smile. So it's obviously frowning here. So this is all part of concave down. And then somewhere over here it goes from a frown to part of a smile here. So right about, let's say, here, it's concave down, and then it switches to a smile. So now the function is smiling from here to here, and then it switches back to part of a frown, so it must be concave down. And so we're concave up on a little piece from, this is probably -1/2, nice point between a nice point between 0 and -1, so let's say -1/2. So -1/2 to 0, it's concave up. So right there, it's concave up. So -1/2, comma 0. And then it's concave down everywhere else. So it's concave down from -infinity all the way to -1/2. So -infinity to -1/2. And so I kind of shading the region here to show you what I'm talking about. This -infinity to -1/2 is this region here. and then it jumps, and then it's concave down over here until you get to, well, probably positive 1/2. So union 0, comma 1/2. Notice you don't include the endpoints on any of these. They're always parentheses are used. Some of these are pretty easy to explain why we use in parentheses and we don't close them. I mean, if you look here where you're increasing and versus decreasing, up here, this point, it's sort of a plateau. It levels off, so it's neither increasing or decreasing. Same thing down here. You don't want to include that point right there because it sort of plateaus. For inflection points, now remember, inflection points happen when you change concavity. So it looks like, and in this case, you'd say where you change color. So you go from a frown to a smile right here. Oh, let's use blue for this, and let's use X's. So there's an inflection point, and then I go from green to red. So there's an inflection point. So there's 2 inflection points. So the first point looks like it happens at negative 1/2, and I bet you the height here is probably positive 1/2, a nice point between 0 and 1. So the input is negative 1/2, so we put negative 1/2, and the output is 1/2. Now this is a point, not an interval, and the other inflection point happens at 0, 0, right at the origin. Right, so make sure you realize that these are points here, not intervals, whereas before I've been giving you guys intervals. So increasing, decreasing, concave up, and concave down are all given an interval notation, whereas an inflection point is an actual point on the graph.